Hello guys, in today's video we're going to be talking about rational functions. Now by rational, we need to define that what a rational function is. So if you want to define what a rational function is like dealing with rational functions, we want to go ahead and first talk about why do we need this and what's the purpose of this chapter. Well, the purpose of this chapter is to sketch out rational functions. Now, what are rational functions? Well, rational functions are basically defined as functions, it's f of x, are two polynomials divided by each other. Okay, so we want to go ahead and define rational functions. So for example, let's take an example. Example, f of x is equals to 1 over x. That's the simplest explanation, and then I think it's probably the one that's also given in the Cambridge book. So yeah, that's pretty much the thing about rational functions. We want to go ahead and talk about what they are and how they function and what to do with these. Okay, so you want to go ahead and understand what's happening with these sort of functions. So now, first of all, we need to get a few properties out. So functions like these will have asymptotes. Okay, so functions like these will have a horizontal asymptote and vertical asymptote. So what are these? So these are values of x that will never happen. Values of x that never happen or are not allowed, basically. So for example, in this case, this function, x cannot be equal to 0. Otherwise, this becomes undefined. Similarly, there are values for which that x never reaches a value of y, no matter how much you try. So it turns out that for this particular function, this is going to be that y never is equal to 0. These are a few properties that we're going to be eventually studying. But for now, what we just want to say that the function never reaches y equal to 0 and x is not equal to 0. The reason being that x will make the entire function undefined if it is 0 at the end, right? So you don't want that. So how to go ahead and sketch a function like this? Well, if we take our axes, so from here, I'll try to draw it as nicely as possible, actually. So I'm going to put an arrow. Okay, so let's say these are axes. The reason I'm drawing this really nicely because I want to write a few properties and how we arrive to the solution that we are considering. Notice that x equal to 0 is this line. So I'm going to mark it. First, I want to mark or label my axes. That's y and that's x. So I want to label that this line right here is x equal to 0 and this line right here is y equal to 0. Okay, and what I want to say that the graph would look something like this. It's never touching y equal to 0 and it's never touching x equal to 0. And again, this is for x having all real values. So that's kind of like the domain. And over here, y also has all real values. So in this case, y is greater than, it's actually not greater than. You can put negative values here. Like for example, you could have f of negative 1 is 1 over negative 1. That's still negative 1. So we can say that the graph also has negative values, right? So what turns out is we're going to have a spitting image of the positive side on the negative side of the graph as well. This is what the function looks like. If I'm going to be using a graphical software to represent this, this is what the graph is going to be looking like, all right? So with that being said, what is the function showing me? The vertical asymptote can be found by denominator equal to 0. This is the formula for finding it. And the horizontal asymptote is basically y as x reaches infinity. Now, finding horizontal asymptotes is a bit tricky and can vary. And there are types of asymptotes that we also want to find out. Okay, so we want to talk about those asymptotes a little bit later. We don't want to talk about them right now. So let's go ahead and dive a little bit deeper and take a look at another example. So I want to take a look at another example over here and use the property that we just established. Okay, and I also want to show you a method to find the horizontal asymptote before I write the properties on how to find horizontal asymptotes really easily. Okay, so we're going to be taking a look at the properties a little bit later, not now, but we'll see what happens. Okay, all right, so let's take another example. Okay, so another example is going to be f of x is 1 over x minus 1. Right, so before we sketch the graphs, let's draw our axes first. So we can have this over here, this right here, and this right here. Okay, and again, let's label it. So we've got y and we've got x. So now we're going to go ahead and first find the details about this graph. Right. So first is find vertical asymptote. So we want to find the value for which x doesn't want to exist. And that is, the formula was denominator is equal to 0. So in this case, x is equal to 0. So x is equal to 1. So this is where the denominator becomes 0. That means x cannot be 1. So that is our vertical asymptote. Or in this case, the equation of the vertical asymptote. This is something that you might be asked to find in the papers a lot. I'll just take my tool and move this a little bit more to this side so that we can work with it a little bit more. Got it. And the next step that we want to do over here is find the horizontal asymptote. So I'm just going to draw it with a different color. So we want to find horizontal asymptote. So these are values of y as x reaches infinity, right? But how do we actually find these sort of values and how to work with these sort of values? Well, first of all, what we can say about this equation. So let's take this equation. We've got the equation f of x is equal to 1 over x minus 1. Okay, if we just place f of infinity is basically 1 over infinity minus 1. That's actually 1 over infinity, right? So anything divided by an infinity is going to be a 0, right? Because as the number becomes more smaller, we can say that the value approaches 0. So as numbers become small, 1 over n approaches 0. Okay, so that's the rule that we are using over here. So that's the equation for our horizontal asymptote. That means we're saying that y is equal to 0. So that's the logic behind the first one as well. That if you place infinity, so we're going to be getting 1 over infinity over here. So in this case, if I were to do the calculation, 1 over infinity is ultimately going to give me 0. So thus, it's y equal to 0. That's the equation that we're getting. That's the result we're getting. But again, we don't know what infinity is. It's going to keep going on and going on. And that's a reason it never touches that axis. So during the exam, what we're expected to do is just draw a straight vertical line to indicate the asymptotes. So let's say we have x equal to 1 as the asymptote. So I'm going to draw a line that I would say that is equal to x equal to 1. Okay, and that's my asymptote. Notice that it's no longer the origin axis. So we might have an x and y intercept. So the next step that we want to do after all this is find the intercept. So what we want to do is find intercepts. right? So we want to find the intercepts of this graph. Again, these are not quadratic graphs, so we're not concerned about what the turning points of the graphs would look like or would be. This is a single-powered function graph. So right now, we still need to talk about what is going to be happening to the turning points of the graph. That means the maximum and minimum points. All right. So what we want to say is that to find the intercepts, what we just do is we take y is equal to 1 over 0 minus 1. That's negative 1. So that's going to be 0, negative 1. And you've got 1 equal to 1 minus x. So x minus 1 equal to 1. And we could say that x equal to 2. So 2, 0 is going to be my x-intercept. Now, we're not done yet. We want to go ahead and find a little bit more about this graph and how this behaves. So what I want to do is I'm just going to go ahead and push this a little bit to the top. It's a little bit difficult to take this. Okay. I'm going to take my eraser, raise these up a little bit. All right, this is x. Okay, so what we want to now find out is another detail is how the graph behaves. So what do you mean by how the graph behaves? So notice that we've got two sides to the graph, this side and this side, right? These are the two sides. So I want to see that how do the equation behave on both sides? Well, it could be that the graph goes something like this, but as you can see, this shape really doesn't make sense. Or it could go something like this and this probably. This could be it, right? We don't know. The graph could go something like this and let's say this. So this and this could be it. There could be also situations where the graph only intersects the horizontal asymptote once and never comes back to it. And we're going to look at those situations in a little bit later, right? There will be situations where the graph might end up touching the asymptotes once, but that'll only ever happen with the horizontal asymptote. Never in the life the graph will touch the vertical asymptote. That never happens. So always remember that the graph might end up touching the horizontal asymptote at some point in their life. Because the horizontal asymptote is not an undefined value. It's just a value that's defined for extremely large values of x that is not expected to happen. Whereas the vertical asymptote is values where the graph is undefined itself. So that's the difference between a horizontal and a vertical asymptote. So now, before I continue, we want to see that how the graph behaves. Is it like this, perhaps? Or perhaps it's like this? Who knows? So this is the behavior we want to check. So we want to go ahead and finally do check for behavior. So that's the last step. So check for behavior. So we want to see how this graph is going to be behaving at certain points. Okay, that's the purpose, that's the total target of this sketching part. All right, so now if we want to check the behavior of the graph, we first take a positive value that's greater than the horizontal asymptote. So we take x, y, and we take values greater than the horizontal asymptote. I'm just going to write it a little bit here. Values greater than vertical asymptote. Okay, sorry, it was a vertical asymptote, not the horizontal asymptote. I missaid it. So it's going to be 2, and let's say we are taking the value of 0, or let's say we take 2 values, 2, 3, and we take 2 more values, 0, negative 1. So 2 values to test out what's going to happen to the graph at that certain point. So I'm just going to be quickly taking my calculator, and I'm going to be calculating 1 over 1 minus x. So the first value of x is going to be 2. That's giving me a value of 1. The next value is going to be 3. That's giving me a value of half. So it's decreasing, as we can see. And then we're given values of 0, which is going to be negative 1. And then we go to minus 1. So that is going to negative half. So the value is technically trying to increase. So what does it mean? It means that the values starting from 2 to 3 are on the positive side. So let's say if this was like 2, so this would be 1, and then this would be 3, and that would be the next. So the graph is behaving like this on the positive side. if I take a look at the negative side, let's say this is 0, so I'm going to get -1 over here, let's say, and then I'm going to be taking -1 and taking a negative half. This is, let's say, -1, this is -1/2. So the graph is behaving like this on the negative side. So after testing the behavior, I've confirmed that the positive side goes like this, and the negative side is going like this. And we also know that our x and y intercepts are here. So 0, -1 is exactly here. So that's one other clue. And the positive, or the value for x, is somewhere here. All right, so that's going to be the value of x is 2, 0. So okay, so this is a little bit strange. Did we do the math correctly, actually? Because this does look a little bit confusing to me. Probably we did the math wrong somewhere, did we? So we've got -1, so that's 0, -1, so 0, -1. And then we've got 2, 0, that's over here. So does it actually make sense? Did we mess up somewhere through the calculation process? Okay, let's try to do this. Oh, why do I? Okay. Oh no. Why did I make that mistake? I wrote 1 here. This should be a 0. So this ultimately is not technically valid. All right, because again, we cannot do, so 1 is not equal to 0, invalid. And we cannot take x to that side or calculate x equal to 1, because that's also not possible. So we have no solutions to this equation. So no x-intercept of the graph. So the graph never touches the x-axis because y is equal to 0. So it's trying to approach there, but it's just not able to. So if I were to now sketch the graph, let's see what color I use. I use the blue, so I'm just going to use the blue here as well. It's going to be something like this, and then it'll touch the graph at only one particular point. Sorry, I'm going to move the ruler. This point, so it's going to touch it right here, and then continue straight on. So this particular point is going to be 0, -1. That's it. And we have our asymptotes, which is going to be the line x equal to 1 and y equal to 0. So these are the asymptotes. So we sketched two fairly simple looking quadratic, not quadratic actually, like very two simple looking curves. Now let's move on to a place where we're going to be having horizontal asymptotes of it at all. And there are a few ways of doing it and how we can figure out what is it. So first, let's go ahead and take a look at it by calculating the horizontal asymptote. And then after doing that, we're going to be coming to a conclusion for the horizontal asymptote, that when and how the horizontal asymptote is going to sound and how is it going to look. So with that being said, we want to go ahead and sketch the graph. So for example, so I'm just going to put an example. So example, f of x is basically going to be, let's try something a little bit interesting. Let's try it a little bit difficult, I guess we could say. So what we want to do is, let's say that f of x is defined as x plus 3 and x minus 5. Okay, so we want to go ahead and define something like that. And after that, we're going to be coming up with two specific properties of the graph. Okay, and how the horizontal asymptote is going to look depending on what the graph is, or how the equation or the polynomial actually looks like. So what we want to do here is, again, we want to follow the similar steps that we just did. So let's just draw the axes first. That makes life a little bit easier for us. I'm just going to erase these. So right here and right here. So y, and then you've got x, right? So we've got these. So first trick is we find vertical asymptotes. Find vertical Remember, in the exam, you want to do these in your mind, or you could label each of your steps. That's not a big deal. They're not going to probably deduct your marks for labeling things. But we want to make that process efficient and fast as possible. So the denominator is equal to 0. Okay? So over here, x is 5. That means that x can never be 5. So that's my vertical asymptote. So what we could easily right now do is just draw a line near x equals 5, right? So, yeah. Let's just draw x equals to 5. So it's probably going to be somewhere here. Okay, that's done. That's it. Now let's go ahead and find the vertical asymptotes. And here is where things are going to get a little bit tricky, right? We want to go ahead and see how the graph is going to perform, right? So how does it get tricky? Well, let's consider the fact that we have over here, right, is going to be that so we want to go ahead and find horizontal. So that's the next target. And we also want to say that horizontal asymptote is the value of y when x reaches infinity. But the problem is, how do we achieve it here? So let's take the function f of infinity. So we want to go ahead and plug in infinity plus 3. And we want to do infinity minus 5. And now what? Now what happens? And how do you actually counteract it? Right? So you want to go ahead and find that for sure. Notice that anything plus infinity is still going to be an infinity. And divided by infinity is still going to be an infinity. Right? And that's totally fine. And we want to go ahead and come to conclusions that we can go ahead and perform similar calculations to graphs where we can easily just use infinity itself and then do the problems, right? So now what's going to happen? And happening is that infinity divided by infinity is going to be 1 because it's literally the same number. So y is equal to 1, right? That's the purpose, or that's the thing that's going to be happening. And we can conclude that this is going to be the horizontal asymptote. There's another way to do this, and the preferred method that you would want to follow if you were trying to find the horizontal asymptotes, because there might be cases where just using infinity or plugging it in is not going to help. You might have something like infinity plus infinity or stuff like that. So how do you do that? Well, first we need to modify the function slightly. And the rule is always to divide, to multiply with the inverse, not actually the inverse, like to the power 1 of the variable. So let's say we have x plus 3 in this case and x minus 5. What we want to do is we want to go ahead and multiply 1 over x to both the numerators and denominators to make it equivalent. So this is going to be changing the function to just 1 plus 3 over x divided by 1 minus 5 over x. So now if x reaches infinity, so that's basically saying what's the limit of function if x reaches infinity of f of x. So if we plug in infinity to this function now, and anything divided by infinity is a 0, so plus 0 and 1 minus 0, it's ultimately going to be 1. So that's the proper way to do this. So there might be cases where you might be never able to plug in the value, but that's literally the most appropriate way of getting this. But we're going to look at a few properties that's going to let us establish that we don't need to do this every single time. And doing this every single time can be a tedious process. And we want to go ahead and find out how to improve on this and not do the same thing every single time, because we're going to be looking at a few properties from this. So now the horizontal asymptote turns out to be 1, right? So let's go ahead and put a mark at y equal to 1. So this is y equal to 1. So these are our new asymptotes. It's no longer 0. Next, our turn is to find the intercepts. So let's go ahead and do that. So find intercepts. So find intercepts. I'm going to keep some space on this side because I want to go ahead and write a few properties out. So for the intercepts, first is obviously y equals to 0. X equals to 0. So we've got 0, and our equation was x plus 3. That's going to be plus 3, 0 minus 5. So that's going to be negative 3 over 5. So that's about minus 0.6. So that's going to be 0 minus 0.6. And we've got 0, and you've got x plus 3 and x minus 5. So we cannot have x equal to 5. So we're going to just take that to the other side and make it a 0. Like, even though we're going to be having two solutions to this, one of them is not acceptable. So over here is going to be 3, 0. Right? So that's the catch. And finally, we want to see the behavior. Okay, so we want to see how this behaves. So we could go ahead and find the behaviors right here. So what we want to do is take the values a little bit above and below the horizontal asymptotes. Okay, so we've got x equal to 5. So we take 1 or 2 more than the vertical asymptote. So the rule is we take 6 and 7, or you could take 3 as well. It really doesn't matter. We want to see how it behaves. And we take values less than 5. So let's say we have 4 and we've got 3. And I want to see how the graph will behave. So in this case, once we have 6, we've got x plus 3 and x minus 5. We want to go ahead and put this in our calculator. And once we have x is 6, the value is 9. When x is 7, the value is 5, it's decreasing. When the value is 4, it's negative 7. And when the value is 3, it's negative 3. All right. Okay. So you could also use your calculator tables. Any way you want to calculate it, just we need a few values to test. So on the positive side, if we have, let's say, 6, so if we take 6 over here, this is going to be 9. And if you take 7, let's say this is 5. So the graph is behaving this way. All right. Then if you take 4, we have minus 7. So let's say this is 4 and we've got minus 7. And if we take 3, we have minus 3 that's over here, right? So minus 3, minus 7, that's behaving like this. This is how the graph is going to behave. So this way and this way, right? So that's the two ways the graph is behaving. And we also have the intercepts on the y axis, and we also have intercepts on this axis. So we've got two intercepts now. All right, that's totally fine. So how do we sketch the graph now? Well, it's easy. So all we need to do is we just take this, and simply sketch, never reaching. Obviously, it's drawn by hand, so don't expect to get a graphical calculator out of me. So x is minus 3 and y is 0. Okay, and y is minus 0.1, x is 0. So it's probably going to go something like this, the best I could do. So over here, we've got one of the intercepts. That's x minus 0.6. That's one of them. And we've got this one right here, which is minus 3, 0. So that's the two intercepts. And that's how this graph will look like. All right. So now we want to go ahead and establish a few unique properties. All right. So a few unique properties in order to make life or make things easier for us to ensure that we're drawing the functions more quickly and more efficiently when we are doing so in the exam. All right. So they just make things easy for us. We're going to be taking a few approaches. So with that being said, now we want to take look at a few properties of horizontal asymptotes. Okay. So I want to just go ahead and write it down, that properties of horizontal So notice that if you have no variable on the top, okay, so the format is, in the first case, that f of x is any arbitrary constant divided by a polynomial, if that's the case. And note that and f of x is a proper fraction. The property that we are seeing is that y, the horizontal asymptote, is always the x-axis, or basically y equals 0. So horizontal asymptote, in this case, the horizontal asymptote always 0. So basically, the horizontal asymptote is y equals 0 in that case. That's the first property. The second thing we just noticed, that if we have degrees of power that is equal, that means we have x's on both of the sides, okay? X's on both sides. We establish the fact that f of x, in this case, if we have p of x and q of x, where x of p n plus whatever it is, and x of q n plus whatever it is equal. So if is n equal to n, that means we are having the same power. We also see that the horizontal asymptote is always equal to y is equal to 1. Okay, you're always going to see the property, because what's going to happen is ultimately, if you're placing infinity on the x's, no matter what the power is, x squared, x cubed, the highest power is always going to have the highest probability. Let's say you had, I'm just going to do some rough, x squared plus x plus 1, and 3x squared plus 5x squared plus 1. Let's say we had something like that, okay, in mind, or something like that was there. Okay, so what is going to be happening? Okay, how are we going to be achieving this function? Well, notice that if you're placing infinity on all of them, let's say we're going to place infinity here. 1 really doesn't matter when you're doing infinity, so that marks out. We were placing infinity here. This will technically still be a larger value because you have a square on that. So ultimately, this function will approach x squared over 3x squared. This is approaching that because these will become negligible at infinity. Only these with the highest power remains, right? That's going to be the remains of it. So notice that if we have no coefficients, right, no leading coefficients, what we can establish from this particular circumstance is that we're going to be having something like y is equal to y, right? So what we can establish from here is that we just cancel these out, and ultimately the asymptote is going to reach 1 over 3, right? So the horizontal asymptote will depend on the coefficient. That's the main thing that I want to establish. In this case, this was 1. If it wasn't 1, if it was something else, then it would have been completely something else, right? That's what I'm trying to establish here. So what we are saying is that horizontal asymptote is y equal to a over b. So what is a and what is b? Let's say that I'm just going to take the yellow color, and this is a and this is b. Y is a and b, and that is going to be by note. Okay, so these are the two properties of horizontal asymptotes and what we want to take. But we want to take a look at a few more properties. So these are just a few. So what we want to do is we want to make more statements. And what if x, the powers are not equal? What if one of them is greater and one of them is, kind of lesser than the other, right? So what we're trying to say is that what if it's less than that? Okay, we want to establish something like that. Well, we're saying that x is proper, right? So if this is the case where I'll just do the same thing, that f of x is p of x divided by q of x, where a x p n plus ... divided by b x q. All right, so we've got x q. Let's say this is m plus ... and n is less than m. What is going to happen in that sort of situation? Where are you going to go? All right. So what I want to take a look is, I want to take a look at this with an example. All right. Let's say we had 3x plus 1, and we'd got x squared plus 2x plus 2. If this was our particular function, then how would it behave in certain scenarios, in certain situations? Well, let's go ahead and do our rule. You're going to be multiplying it with 1 over x on both sides, all right, both the numerator and denominator. So what you're going to be achieving is 3 plus 1 over x. Then we're going to be achieving 1, just x actually. So the problem is if we achieve just x, we're going to be ending up with an infinity at the bottom anyways, which we don't want to do, right? Which we don't want to do. Or even if you have done that, that's really not going to put an effect to the entire equation. Why is that? So if we were achieving, let's say something like the highest power of x, let's say if we were not doing that and we're doing x squared, to remove the square terms completely, we're going to have 3 over x squared. This is totally gone. That's a 1 plus 2 over x plus 2 over x squared. And as x reached infinity, all of these are going to be approaching 0. This is basically we're doing different integrations from infinity that we did on mathematics AS, right? We had these implicit integrations or improper integrals that we had infinity. So we wanted to look for a situation where x is in the denominator and then make those 0. Right. So notice that you ultimately end up with a 0 over here plus 0 over here. We had a 1 plus 0 plus 0. So it's still coming out to be 0. So even if the case that means that this is still a proper fraction because the power is smaller than the denominator, you're still going to have y equal to 0 as the asymptote. So that's a property we're looking for. So what we want to do is we want to take this. So we want to say that horizontal asymptote is y equals 0 once again. All right, that's the thing that we are looking for. That's the property we're trying to establish right over here. All right. Well, let's move on to the next part of the problem. We want to take a look at what if that's the case with the fraction is improper. In that case, we come up with a new thing known as oblique asymptotes. And when we're coming to stuff like oblique asymptotes, we want to look at much more difficult, let's say, what do you call it? We want to take a look at much more difficult rational functions. Functions where, you know, it's going to be touching the asymptotes, or one of the asymptotes. That's obviously going to be the horizontal asymptote. We're going to have turning points, and we also want oblique asymptotes. So before we move on to oblique asymptotes totally, I want to go ahead and give you one more example before we move on to them completely. So I'm going to put them over here, and we want to do our final example problem without oblique asymptotes. And what are oblique asymptotes? We're going to find those out pretty soon. Don't worry. So let f of x equals y equal to x minus 1, x minus 2, and then we have 2x minus 1, and we have x plus 1. Notice that this is going to be a quadratic equation, and we want to use certain properties of the function. So since we want to go ahead and use certain properties of the function, what we want to do is we want to go ahead and find in total that in this particular function, how many turning points we're going to be having since it's a quadratic function, and we want to also take a look at the properties. Now, if you are going to be going ahead and expanding this function a little bit, this is going to be turning out to 3x plus 2 over, we're going to have 2x squared, and then we're going to have plus x and minus 1. Okay, so this is the function that we're going to be turning out to have. All right, so notice that we have the same power, right? So xpn is divided by xqn, and n are equal. So what we can already establish that the horizontal asymptote is y equals 1. And that makes things easier for us, right? We don't need to go ahead and do the tedious calculation or understand that we have any special circumstances regarding y. We really don't need to do that. So that's pretty much done. That's one thing you can use the properties for, making things easier for us. right? Okay, so now what we want to do is we want to go ahead and first draw the axes. So I'm going to draw the x-axis, erase this a little bit, and I also want to draw the y-axis. Sorry, I just messed those up, the y and the x-axis actually. Okay, so first we want to go ahead and find the vertical asymptote. So the first step is to find vertical asymptote. And notice that now things are a lot harder. We have two sets of vertical asymptotes. So now what should we do, or what is to be done? Let's find out. So we've got the denominator must be equal to 0. So that's the first law, that's the first rule that we want to follow. So we put it equal to 0, just like this. Okay? And then the values of x are basically half and x is equal to -1. So these are the two vertical asymptotes. Okay, that's the first property that we've established. So since we have found out the two values of the vertical asymptotes, what we can simply now do is just, let's say, sketch them. So we first got a half, so that's going to be right like this. That's x equals half. And then we also have x being a 1. So x is equal to -1, actually, not just 1. Right? We want to kind of do that. That's the vertical asymptotes. So now we want to go ahead and evaluate the horizontal asymptote. Now, note that if we have the same powers, right? Even if we have the same powers, and if it's less than that, it's technically not exactly 0 as well. Why? Even though I just established it is. Well, if you take a look at this closely, right? If we take a look at this closely, this is still going to be a over b, rather than completely being 0, where this is just an arbitrary constant. The reason being that if we take infinity squared on, the a values ultimately, we still end up having to do with this. So what is going to happen is, this is a common question among students, is that, okay, so we end up having infinity squared. So we've got we've got a1 over x, which is turning to 0. So that's the reason that if this entire thing is 0, this evaluates to 0 ultimately. So what is going to happen is this is going to remain as 0, not a by b, because I heard a few questions that students were confused between, then what about these, right? So that's the reason it remains to be 0. So the horizontal asymptote is basically going to be that this is flat. So in this case, we've got the same powers. So the horizontal asymptote is not actually 1, it's rather, we've got a 2 over here. So that's rather a over b. That was a format. So it's 1 over 2. So the horizontal asymptote is a little bit incorrect. So the asymptote in this case is going to be 1 over 2, not just 1. I apologize for my mistake. So if we have 1 over here, so let's say this is half. This is y equal to half. So now we have the shape of the asymptotes. So now what I want to determine is how is going to be the function, or how the function is going to look and it's going to behave, and how many turning points the function is going to have. So the first easy thing that's easy to establish is the turning points of the function. All right, it is easier to kind of find the turning points of the function. So how do we do that? Well, what we want to notice here is that the graph is going to have turning points. So let's first find the turning points. The turning points. So you want to find the turning points. We need to do df of x by dx, right? That's the rule. So if you are doing df of x over dx, so we need to go ahead and use the chain rule, right? So that's going to be vu prime minus uv prime over v squared. That's equal to 0. So if we were to do the chain rule, we are going to be having v plus x minus 1, u prime, that's going to be 2x minus 3, minus u, in this case, So that's going to be we're going to be having x squared minus 3x plus 2, and v prime, which is 4x plus 1, divided by v squared. We don't need this because ultimately we're going to be validating it to 0. So we're going to be having a cubic equation for this ultimate value. You're going to be having a cubic equation over here. And notice that, okay, we are actually not going to have a cubic equation because we've got 4 and you've got 1, and you've got 2 and you've got 2 over here. That's 4x cubed minus 4x cubed. So that's going to be canceling out. So you're not going to be having a cubic equation. I'm going to simplify things for us, and I already have it solved. So that's going to be equal to 10x plus 1 is equal to 0. So x turns out to be exactly, so over here, that x is going to be turning out to have extremely weird values. So I'm just going to write the values for you. So this is going to be minus 3 2 by 7. So right, so you're going to have plus minus 7. So these are the values of x. The values of y will follow as. So we're going to be having y equal to minus 1 plus minus 2 root 2 over 3. So these are the values. Now, what we want to establish is where are the turning points of this asymptote, right? Is it going to be, let's say, on the negative side or on the positive side? Notice that turning points could be possible anywhere, right? It could be that the turning points are over here as well. It could be here, it could be here, it could be here, it could be anywhere, right? So notice that this is 0.5. So I'm going to write the decimal values of these right here. So for the values, what we have over here, basically, the turning points. So if I do take my calculator once again, and I type in 3 root 2, and I do over 7, that's going to give me 1.32. And the other value, if I take the negative version, so the other value is going to be giving me 1.08, right? And this is 0.5, right? So this right here is 0.5. Oh, sorry, this is actually 0.108. So one of them is actually, okay, it's over here. One of them is actually greater. So it's probably going to be somewhere here or here, which we don't know yet. We've determined that one of them is going to be in this region, because over here, if I do the same values of y as well, if I am to find the values of y, for 0.32, that's minus 0.00572, and for x, that's minus 1.94. So if we have a positive x and we've got a negative y, that means one of the points is somewhere, oops, I pressed the ruler again, is somewhere here. The other point is going to be, let's say, you've got 1.3 and minus 0.75. So the other one is going to be minus 1. So let's say this is somewhere 0.1, and you've got 9. So the other point is going to be here. So you've got two values. One is here, the other is here. So now what? So this is where things start to get a little bit more confusing. We want to go ahead and find out that how the curve behaves. And that's necessary in this particular scenario, in this particular case. So what are we going to do in a situation that's like this? All right. So now our final thing is to work with how the curve behaves. I'm going to be erasing the horizontal oblique asymptote thing for a while. I want to see how the curve behaves. So let's go ahead and see how the curve behaves. Behavior. All right, so we want to go ahead and test out the behavior of this curve. All right, so that's something that we want to test out. So the curve is going to behave in the following manner. Again, we take the two vertical asymptotes, and since we have two of them, we want to take a soothing value that's between this All right, so that's the value that we want to take. So by using my calculator, I've established that when x, so we want to take values that's less than minus 1. So when x is less than minus 1, y is greater than 0. Okay, so when x is less than minus 1, y is greater than 0, and the value is decreasing. So this is something I've found out with my calculator. So what I can say is the graph, when it's this, y is greater than 0, and the value is decreasing. So that's how the curve looks like. Okay, so you could test it out by taking a couple of values, right? We could take x, y, and we could take values, let's say minus 2 and then minus 3. Okay, and then we can plug it in. So we've got x minus 1, we've got x minus 2. Just plugging this in my calculator to see what values I get. So in this case, if I have x is equal to minus 2, that's giving me 2.4. So it's a positive value. And it's also on the positive side, since we have just established. And we're taking 1.4, right? So with that being said, we know that the curve is behaving like this, somewhat like this. Okay? Now we want to establish that what is beyond this, right? We want to find what's beyond this point of the curve. So what we want to say that if the value is greater than, and again, if you're asking me how do I know this, I've solved this math before, so that's how. Okay, and what I've also found is the value is decreasing, followed by an increase. Why? Because notice that if it's increasing, then we should increasing, and then if the value is greater than 0, and if it's decreasing, we should again get a shape like this, but we also have a turning point. And the turning point is somewhere here, right? Oh, we still didn't find the intercepts. Okay, I forgot to do one major thing. The intercepts of the graph that we're going to find out very soon is that if the turning point is somewhere here, then the graph has to somehow, if it's shaped like this, cross the asymptote once and then turn. And remember, all asymptotes are crossed only once in their lifetime. So if it crosses it over here, it's going to go to its turning point, and it's never going to touch it again. Or it could be that if the graph is decreasing, that has to be it. Because again, if you're trying to draw it like this, it's never reaching its turning point. We just found out the turning point of this coordinate right here, 1.32 is minus this. It's gonna have to shape like this. So we are noticing a property that some graphs may exhibit. They're touching their horizontal asymptote once. They're cutting the asymptote once. Again, horizontal asymptote is not an undefined value. It's just a value that x tries to reach but is unable to reach at very large values, or will end up reaching at very or extremely large values. All right, so that's the target that we're getting over here. So what we are saying that it's decreasing and increasing because of the turning point. So why is that? I'm going to label it as because of the turning point. So because of turning points. Turning point. So what we are seeing is that if we take two random values, I'm going to take two random ass values of this. So we got that x is 0.5. So let's say we're taking 0.6, something this, and let's say we are going to go ahead and take 0.7, and we're going to take something that's greater than the turning point right here, 1.32. So let's say we're taking 1.35 for sake. So we're going to do 1.6. So that's turning out to be 1.75. We're taking 1.7. That turns out to be 0.6. Okay, and we're taking 1.35. That turns out to be negative 0.05. 0.06 actually. Notice that this is this is actually 0.0. So what we're seeing is that the turning point is 1.32. So beyond the turning point, this is 0.06. Okay, it's actually 0.56. So this is, notice that this is 0.57 and this is 6. So what we can say is, let's say this was the turning point. Let's say this is the turning point. Let me erase. This is the turning point. So the graph comes here. This is 0.57, and over here is 0.56. It's increasing back. So this is how the shape of the graph is going to be here. We have determined this is how the shape of the graph is going to be here. Now, what about this region? Does the graph stay on top or on the bottom? And that's what we need to find out. So we take any range of values between this, right? So what we are saying is that x, when it's basically greater than 0.99, so we're saying that when x is actually this and greater, we're saying that this, in this case, the values of y tend to be less than 0, right? So the values of y less than 0. And similarly, when x is less than 0.4, or that means actually less than 0.5, right? Because this is 0.5. So it's actually less than or equal to 0.4. So any value is 0.5. That's not the correct notation. What we should use is something like this. When x is less than 0.5, y is also 0. So what is happening over here? That shouldn't happen, right? Well, you're not wrong, but the property is, again, increase to decrease. And we find this by taking values of the turning points. Okay, values less than or greater than the turning points. So what are the turning points? Again, this is becoming a lengthy math, but if you want to manually sketch this without a graphing calculator, that's what you need to do. So we've got x, y over here, and then we're going to be having, let's say we have the turning points, 0 point whatever. So the turning point is somewhere on the positive side, right? It's somewhere over here on the positive side. So what we can do is we can take values less than that. So we're going to be taking 0. We're going to take a value greater than 1. So that's -1. So that's actually 0. That's totally fine. So that's also less than the turning point. And then we're going to take a value that's greater than the turning point. So 0.18. So I'm going to take 0.2 in this case. Okay. And we know that these are asymptotes over here. And the graph, I keep pressing the ruler button. The graph is never going to touch these. So if the turning point is here, the graph is probably going to be a U-shaped parabola because all the values of y, which I found out by calculation, is less than 0. You need to do this on your own. I'm just speeding things up in the video. So if I plug in the values of 0, I get -2. And if I plug in 0.2, I'm also getting -2. Okay, fine. Let's take 0.4. So I'm getting -3.4. If I had 0 and I have -1, let's take -0.5. So if I'm taking -0.5, that's -3.75. And I take positive, that's if I take positive, that's never going to work, right? If I'm taking negative, that is working. So it never reaches that value, but that's never going to work. So what I can see from here, if I try to explain it a little bit, that let's see if we've got 0. Right, x is a value of 0, y is -2, and x is 0.2, so it's somewhere over here. Y also has this value, right? And then you've got 0.4, so y is over here. So we can see that the graph is behaving like this, right? That's the behavior. So it's going to be a turning point shaped graph, where this is the turning point. The last thing, after I've figured out the shape, which is going to be this, this, and this, we want to figure out the intercepts of the graph. That's the final and last thing to do while sketching the graph. Okay, so you want to go ahead and do intercepts. So if you wanted to go ahead and do the intercepts of the graph, what we could simply and easily do over here is a very simple calculation, right? So we have y equal to x -1. I'll take the math from my computer. X -2, then we've got 2x -1, and we have x plus 1, right? So intercepts, so when y is equal to 0, we cannot take this equal to 0 because that's invalid, so we're not going to do that. We're just going to take the top. So we have two intercepts, x is 1 and x is 2. And we want to find the corresponding y values. So when x is 1, y is 0, and this is also 0. So basically 1, 0, and 2, 0. So those are the two values that we want to find out. Notice that this is one of the intercepts near the this right here. So if this is, like, let's say Uh, so this right here, if this was the case, we've got x. So we have got two x-intercepts. So one is x equal to 1. You've got a turning point, and then x equal to 2. So see, it's perfectly matching with how we predicted the shape was going to be. We also want to find out the value of y when x is 0. What's the value of y? So when x equal to 0, y is basically going to be -1, -2, -1, +1. So we are going to be having -2. So basically it's going to be 0, -2, right? So finally we are done. All we need to now do is take our pen and sketch away. So it crosses the asymptote once. So what you can do is you can predict what the value of the asymptote is going to be by solving it, but we're not going to do that. We don't need to. I'll try to draw this a little bit more nicely. Trying not to touch this. So right here is going to be our value. It's going to be 0, -2. Right? It's actually less than the turning point, which we found out to be not turning point actually. It's a little bit to the left, which is right here. So that's going to be this, and it's -1.94. So it's actually above 2. So that's probably our turning point, right? Okay. With that being said, this is going to be 1, 0, and this right here is 2, 0. This is a turning point, and this is a turning point. And that's how our graph is going to look like for the following equations. All right, so let's finally go ahead and talk about oblique asymptotes. And by oblique asymptotes, we're talking about curves or that will have asymptotes that are not straight lines. So they're not exactly horizontal. They're like straight lines that are the asymptotes of the curve. And there are a few conditions. All right, so first let's go and understand what an oblique asymptote is. So if we want to go ahead, so the property is that, the first property is if f of x is going to be a x, let's say we have p of x over q of x equal to axp squared, or let's say we've got n plus 1 is oblique. If f of x, where is p of x and q of x, that's going to be n. Let's call this m. And n is greater than or equal to m plus 2, then we're going to have no horizontal or oblique asymptote. So that's the property that we're now going to take a look at, and how this works and how to find the oblique asymptote. So finding oblique asymptote. So in this case, to find the oblique asymptote, what we're just going to do is we're going to be taking an equation. In this case, let's say f of x is equal to x squared plus 1 divided by x minus 2. So notice that the power is basically n plus 1. Like let's say this is 1, so this is 1 plus 1 equal to 2. If the power was 1 plus 2, which is 3, then we would have no horizontal or oblique asymptote. We're not going to have any asymptotes. But the condition is always needs to be n plus 1. That's the condition for an oblique asymptote. So to find the oblique asymptote, we simply do long division. So the method is do long division. So in that case, what we're going to be having is x minus 2, then we've got x squared plus 0x plus 1. So you got x, so that's going to give you x squared minus 2x. So we're going to be having plus 2x plus 1. So we put plus 2, that's going to give me 2x. And then we're also going to be having right here, that's going to be minus 4. So yeah, so the remainder is 5. We've got the remainder as 5. So the oblique asymptote in this case, is going to be y equal to x plus 2. So this is your oblique asymptote. So this particular solution is the oblique asymptote of the equation, right? And this is the case for all oblique asymptotes. There's also one other way that you could end up doing this, and that would always be by doing it in partial fractions. And the format for that is going to be ax plus b plus c x minus 2. All right, so it's either this or this format, and you do perform partial fractions. All right. In this case, that this could be any polynomial. That's what will mean q of x. So these are the two ways you could do it. I still find that it's easier to do long division. And ultimately, we are doing partial fractions. But it's just that you need to go ahead and find, oops, I'm clicking the ruler again, find this, which is a little bit tiresome. But again, if you want to do it that way, that's also fine. That you could use partial fractions and find the value of a and b, and that's going to give you the exact same value as this. So now let's go ahead and try to draw this graph. Okay, so let's try to draw this curve in this case. So let's try to sketch. So let's do sketch f of x is equal to x squared plus 1 and x minus 2. So in the cases, let's first go ahead and draw our axes. Just going to use my white ink. Right, like that. Y, x. So we know that our oblique toad is basically y equal to x plus 2, right? This is y equals x plus 2. We can also find the vertical asymptote. And that's always a denominator is equal to 0, so x equal to 2. All right. Make sure you're making your workouts as short as possible for the purposes of the exam. Now, what we want to do is we want to also go ahead and mark them in the graph. So we've got x equals 2, so that's approximately this line right here. So that's x equal to 2. And you've also got your oblique asymptote that's going to be passing through 2. Also passing through some value here. It's not necessary to find. You could do it, but that's not required. It's probably going to be minus 2. So now, the question is, how is the graph going to look like? All right. So now what we want to go ahead and do is we also want to find behaviors of the graph once again. Right? We're going to take a look at the behavior of the graph. So before we take a look at the behavior, we also need to find the intercepts. So let's go ahead and just do that. So we're going to go for intercepts. So
if we have x squared plus 1 equal to 0, so this is when y equal to 0, x squared is minus 1, and we have no real solution. So no y-intercept. When x is equal to 0, x is minus half. So minus half, so that means we're going to have 0 and minus half. So that's probably somewhere here. And we have two oblique asymptotes. So since we only have one intercept, that's going to be 0 and minus half. That's somewhere over here, right? So we want to go ahead and see that what's going to be happening over here. So x squared, so we're going to be putting that that right here. So x equal to 0 in that case. All right. So what we're going to be doing is simple. Okay, so we've got 0, and we've also got minus 0 and minus half, right? So that's the thing. So we know that we have got 0 minus, so that's somewhere around here, right? 0 and minus, that's somewhere around here. So we have our equation of the oblique asymptote. So if you want to go ahead and sketch the graph of the following, we need to find the behavior. All right. So in this particular case, we have 0 minus half. So that's going to be somewhere here, right? That's the value. I was actually pointing to this. I don't know why. This is the value right here. So we know that our oblique asymptote, in this case, we only have one y-intercept and we have got no x-intercept. So when we have oblique asymptotes, usually the curve lies between the asymptotes, which is here and here. That's the general rule, all right? It could also lie somewhere here, but we don't have any x-intercepts, so that's not possible. We don't have any y-intercepts, so that's also not possible. So the only logical possible path is going to be, if the asymptote's here, the curve looks like this, because these are going to be spitting images. It's either here, 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 or that's pretty much it. So it's going to be either one. So in this case, this one makes more sense. So what you could do is you could still find the turning points. Let's do the differentiation, or directly sketch a graph. See, if I were to just sketch a graph, this would look something like this. And I would say that, all right, this is where it's intersecting, and probably like this. But it's always better to see that if we have any turning points. That case, the turning points are going to be this and this, if you want to find them, actually. But this should be the shape of the graph.
All right, so the next type of curve that we're going to be looking at is, let's say we have no vertical asymptotes. And what that means specifically is, like, let's say you've got the curve y equal to x squared minus x minus 2 divided by x squared minus x, and then you've got plus 5. Now notice that if we take, so consider x squared minus 5 plus equal to 0. This function right here has no real solutions, or what you could say is roots. So in this case, this means since x squared minus x plus 5 is not equal to 0, there are no vertical asymptotes. And there's no direct way to figure this out, even though in the previous slides we've seen that maybe if they're probably kind of equal, you might end up having a vertical asymptote and a horizontal asymptote that's like just one or itself. So in this general case, it's usually the fact that you kind of have to calculate it first. And if you're seeing that if it's not equal to 0, you're not getting any real solutions through a calculator, all you simply need to do is that, okay, that means this right here, is basically, what do you call it? Like this thing has no vertical asymptotes because like it's not equal to 0. So now what? So what we're going to be doing is we're going to be still trying to sketch the graph of this. This still might have a horizontal asymptote because as you can see that we do have a power from our conditions that we have previously specified, is that it has to be either n plus 1 over right here. Okay, sorry, this is for oblique asymptote. So basically, if we have, I don't know if I've written it. Yeah, I have written it right here. So as you can see, like we still have equal powers. Then like we still have like a horizontal asymptote for this. Okay. And there's a direct way of doing this as well. Like this is going to be ultimately like my horizontal asymptote. So in that particular case, what for this particular function, the horizontal asymptote. So if I actually just kind of write it according to formula, according to the formula, the horizontal asymptote is a over b. So therefore 1 equal 1. Therefore the horizontal asymptote y equal to 1 is horizontal asymptote. Asymptote. But if we want to prove this, okay, let's say I want to prove this. So for proof, what we are going to be doing is consider the fact, consider the fact that we kind of go ahead and try to solve for this particular equation, or this particular what do you call it, the particular root. So for example, you have got y equal to x squared minus x oops, sorry, how to undo stuff. Okay, right here. Then we've got minus 2 from the equation, and then x squared minus x plus 5, right? Okay, so now multiply everything out. So we've got plus 5 equal to x squared minus x. Then we've got minus 2, right? Then let's just start factoring out everything. Yx squared minus yx plus 5y minus x squared plus x minus 2 equal to 0. From here, what we can simply do is just take y minus 1 x squared. Then we can take plus 5 minus y, and 5 minus y x plus 5y 5y oh, this is going to be plus 2 equal to 0, right? So since no real solution, why? Because notice that this is the same, like the x squared x and where was it, whatever this is. So basically this is the exact same function as this one, right? So this is not going to have any real solutions. Or you could kind of try to plug it into a calculator and try to figure it out and see what is eventually going to happen. So that's also an option. So what we could ultimately do over here, or from here, is, since this is like has no real solution, we could do is minus 5y squared minus 4 minus 1, and 5y plus 2 is less than 0, right? Now, luckily, just to save time for the video, this is already solved in, I think it's also solved in the book. It's 19y squared minus 10y minus 9 is greater than equal to 0. That means this proves that y is greater than 1 and y is less than minus 9 by 19. So these are technically going to be your values of y that that cannot be reached, right? So once the inequality is, so this is the inequality that you are getting from, the y, right? That means in this range, in this range, there are no real roots. Therefore,
roots are in this particular range. Okay, so this is where you're going to be finding your roots. And since we have just said that according to our formula, that this right here is our horizontal asymptote, notice that the root is between 1, which is our horizontal asymptote, and a certain value. This could be a turning point, right? Or a minimum point. So basically what we're saying is that since this is a quadratic equation, obviously we have to go ahead and find out the turning points of the function. Okay, so we're going to be doing that. Okay, so now our next step for sketching the entire function is going to be, so first let's find points of intersection. Okay, so I'm going to do is points of intersection. So we're just going to be taking this, the points of intersection, and from here, what we want to do is we want to find out that when x equals 0, x equals 0, y equals to 0 squared minus 0 plus 2. Oh, minus 2, sorry. Minus 0 plus 5. So basically y is minus 2 over 5. So this is where when y is equal to 0, that's where the graph is intersecting. And we could technically also say that that's one of the points of intersection. Okay, yeah. And when y equals 0, we have 0, x squared minus x minus 2, x squared minus x plus 5. So we could solve it into this, because again this has no real solution. And from here, we figure out that x, by using my calculator, is x is equal to 1 and x is equal to 2. Okay, so we know that our horizontal asymptotes, I'm just going to be going ahead and drawing out a line here. This is, let's say, y equal to 1. And this is also our horizontal asymptote, right? So that means that since this is the horizontal asymptote, the curve can take two different positions. And by that, what I mean is that the curve could have either gone like this, or it could have gone like this. Why do we have a quadratic hump over here? Because this is like a quadratic equation, and we are going to be having turning points, obviously. But the problem is, from the inequality that we solved, we see that it's between 1 and a negative number. That means that the curve has to go from the bottom instead of going from the top. Now, you could say that, okay, what if I didn't solve for the inequality? Well, the next thing we're going to be doing is differentiating the function to see if we have turning points or not, and to specifically see that where the turning points of the function specifically are. So what we want to do is we want to go ahead and just take the function, which is turning points. Turning points. So y is equal to, we've got x squared minus x minus 2, x squared minus x plus 5. So dy over dx is going to be x squared minus x plus 5. Then we've got now also one more thing to particularly note, that this would be a faster method right over here to figure out where exactly the function could technically lie. Or another way of checking the function is, since you now know the horizontal asymptote is like 1, you can make a small table just to see that how the values of x kind of approach. That means like if like you take some values of x, like 0, 1, 2, 3, 4, and 0, minus 1, minus 2, minus 3, minus 4, and check how the value of x would behave. Was it greater than 1 or was it less than 1 every single time? And I think that's an easier method if the question particularly tells you that you don't need to find what the turning points are or kind of mark it in your sketch. If the question specifically tells you that, then it is harder, because now we got to differentiate this entire thing. But again, it's much more easier to just figure it out. You know what? In fact, let's go ahead and just do that just to show you how
easy it actually gets. Okay, so basically we're going to be taking some values of x and some values of y. So obviously 1 is not a possible solution. So what we're going to be doing is you're going to be taking, let's say, for values of x, we're going to be taking -1, -2, 0, 1, and 2. Okay, so since we're taking these particular values of x, what we're just going to be doing is calculating that what the values of x are for this particular, kind of solution, right? All right, so we're going to be just taking our calculators, and what we're going to be doing is I'm just going to plug in. We've got x squared minus x, then we've got -2, x squared minus x plus 5. And the value of x in this case, we're going to first put is -1. So what we want to do is calculate. Okay, so once you put -1, which, oh, it's already, we found out it's already an intersecting point, so that's a 0. I'm sorry for that. Forgot about that completely. Then we want to do is we want to put -2, and that's coming out to be about 0.363. Then what we're going to be doing is for x equals to 0, we already know that this is -2/5. So that's going to be -2/5. And that's going to be -0.4. Then for x equal to 1, so we're going to be doing x squared minus x minus 2, x squared minus x plus 5. So we want to put the value of x to be 1. And that also comes out to be -2/5, or okay, so okay, so at around x equals to 0. So notice that means we are going to be having a turning point here, because we found out that this is the part of symmetry. So we were lucky in a sense that, okay, we already found like where the symmetrical point in the curve is. So that means probably we have a turning point around here. So we don't even need to differentiate this unless the question specifically requires you to specifically point out that, okay, these are the turning points of the function. So in an exam situation, that this is the method I would prefer rather than differentiating the entire thing. But if you do want to differentiate it, like from all this, I can already predict that the graph is going to go something like this, okay? But still, just for the sake of differentiating, what we could just do is v, then we got u prime minus u v prime by v squared. Okay, so dy dx. Okay, this is going to be x squared minus x plus 5, 2x minus 1, minus x squared, minus x minus 2, 2x minus 1, x squared minus x plus 5, whole squared, and you got to solve this. Okay, so whatever the result is, that's going to be your homework. I'm not solving it. But since we've already kind of figured it out that this is going to be it, we already know what the predicted points are. So first of all, let's mark what we can actually use in the graph and kind of plot it as accurately as possible. These 2 points, this particular point, could be used to kind of plot the graph nicely. So if you were to plot the graph now, it's going to be something like it intersects here, and then it has a turning point here, and simply like this. So this point is particularly going to be -1, 0. This point right over here is going to be basically 2/0. I could have drawn it a little bit more accurately, but oh well. And then this particular point right here is going to be your specific 0 minus 2/5. So you've got your 3 points, and this is the most accurate representation as much as possible. So just the table method or the tabular method works. If you want and if you can, like if it's solvable on a calculator or something, you could go ahead and solve this quickly in your exam. Or if you think that, okay, now I'm going to be way too sure about my answers and then find the exact position where the turning points are, this is also so this is also a viable solution. In fact, we can actually solve for this by just doing this 2x minus 1. And then you've got x squared minus x plus 5 minus x squared plus x plus 2 is equal to 0. We could kind of start solving for them. And then we can just simply cancel this out, and 6, 7. Oh, okay. So we technically have solved it to be x equals to half. And for this particular value, I'm going to be going ahead and just changing the value to half. Okay. So the differentiation wasn't that difficult, to be very honest. And there you go. Y is like minus 19 over 19, which kind of comes out to minus 0.473. So as you can see, it's lying between 0.4, right? So it's probably here, like right here is going to be 0.5, and then this is 0.47, whatever the value is. So you could also use differentiation to pinpoint where your graph is going to be, like the turning point is going to come out. Okay, we got a few more things, actually quite a lot more things to cover before we kind of finally jump onto the last part of this, what do you call it, the entire lecture or something. So what I plan to do is introduce those two topics directly by the use of question paper math before we kind of move on. But I think it's also important that before I kind of show you what that is, I want to show you the absolute values of rational functions, or absolute value graphs. So basically, absolute value graphs. Now, this is actually pretty easy. It's nothing to be scared of, or it's not going to be that big of an issue. But we could go ahead and just simply show it to you with not with a complicated one, but with a more simpler example. So let's grab a more simpler example. So let's say that we have y is equal to 1 over x squared minus 1. This is going to be your graph. So from this particular format of the function, we can automatically say that the horizontal asymptote is the y-axis. Or basically, we're saying that y equal to 0. Okay, so that's going to be your horizontal asymptote, because we've seen this from the particular formats of rational functions in our previous problems. So, and we can also say that the vertical so in your examination, the best thing to do is obviously make your mathematics as short as possible, because you won't have time for that. So basically, it's going to be plus minus 1. So we kind of have it figured out. Then we need to find out turning points of the function. Okay, so what we want to do is we want to say that, okay, the turning point, and we also want to find out intersecting points. So let's go ahead and do that. So you've got intersecting points, intersection, or intersecting points, whatever it is. So what we could say that when we have, let's say, x equals 0. So y is equal to 1, 0 minus 1. So y is equal to negative 1. So that could be a point. But then the thing is, the y-axis is the horizontal asymptote. That means we have no y intersections. Okay, that means y is never equal to 0. Because y, that's the horizontal asymptote. Okay, you might be tempted to just kind of solve for, kind of x and just say that, okay, that's going to be my particular, kind of y-intersect, but that's not how it works. Okay, because those are ultimately going to be your asymptotes. So we kind of have a rough idea of how the graph is going to look like, but that's not our concern. So what we want to do is we also want to differentiate the function a little bit. So we want to say that y is equal to 1 over x squared minus 1. So dy over dx is going to be, let's say, so you're going to be having -1, 2x divided by x squared minus 1 squared. Okay, so I'm not going to show you differentiation because I'd assume you would already have done this in your A-level mathematics, just to make the process quick. Okay, so we want to go ahead and find out like simply what the turning point of the graph is going to be. Okay, so from this we kind of have to solve for x equals 0. And we already know that if we are solving for this particular solution right here, this is going to be yielding us to our vertical asymptotes. So the reason is we got to now go ahead and solve for this for turning points. Okay, so this is our turning points, or this is particularly for our turning points. So what we want to particularly do in this case, or this over here, is just find out, or we find that x is equal to 0 is also a turning point. So over here we already know that y has a value of, if I'm not wrong, the value was 1, or oh, it was -1. So this is also our turning point, TP. I'm just going to call that. Okay, so now with all that, we kind of have a picture of the graph in our mind, right? It was pretty easy, pretty straightforward to kind of grasp. So what we want to do is, this is our graph. We've got x equals 1, so x equals 1. X equals -1, and yeah, with that being said, we can now assume that the graph is going to be easy, something like this. You could also do the tests like to figure out like how the shape behaves, but just for making the video quicker, I'm not going to go ahead and bother with the shapes right now. And we know that this is going to be a turning point, so this has to kind of look like this actually. Okay, so now what I want to go ahead and sketch, what I want to go ahead and kind of show you the sketch for is what if we take the absolute value of y equals to 1 over x squared minus 1 and an absolute value of this entire function. We already know what absolute values are. So simply, all you need to do, all we need to do for this particular kind of graph is I just, in our exam, obviously, you're not going to be having an iPad with you, but I'm going to go ahead and paste the same graph in our exam. You could use a pencil and then an eraser, obviously. And all we need to simply do is just, I'm going to use a smaller eraser. Okay. And just flip the graph for the side that is obviously going to be your absolute value. So I'm just going to choose a different color for this, maybe yellow. And all you need to do is just flip the graph to a positive 0, 1. That's it. That's your absolute value function. That's all you need to worry about. That's all we're concerned about for absolute values of that. And that simply goes for oblique asymptotes as well. Like, for example, if this was our oblique asymptote graph that we just drew, and we needed to draw the modulus of this, just simply, if your question specifically tells you to find out what these points are, and if you do know them, just simply sketch the graph like this. That's it. Or this particularly would look something, it wouldn't look something like this, rather it would look something like this. Okay, so make sure the shape you're maintaining it. So this is going to be the shape, because I've seen a few students, including me myself, once did it like this, and that's not correct because we're not following the shape. It's just a mirror image of this exact graph, so you just draw it like this. The intersection point, it just shifts here. This point, it just shifts here, and you just kind of, just raw dog it and just draw that. Okay, so that's how you pretty much draw it. The last thing that we want to see is an inequality problem. But what we are going to do is, obviously, we're not going to be using, kind of an example, but I want to show it to you via a question paper, directly from a very recent question paper, so that we're also done with the question paper practice, and we're kind of also done with the last concept, which is solving inequality problems with rational functions. Now, before I do continue with that, I want to just mention that for rational functions, inequalities don't work like, kind of regular math problems. The reason is that you have asymptotes and rational areas to worry about rather than just solving inequalities like you would do with regular inequality graphs, or kind of linear graphs or quadratic graphs or stuff like that, because or cubic graphs, because you kind of know how that works and how that looks. But for rational functions, it's always best that you kind of sketch the graph first before solving an inequality, and that's how the question papers are designed. So I'm going to be taking a paper from 2025. That's the most recent one, from the summer session, and we're going to be just kind of solving this, and I wanted to show you that how the graph would pretty much look like, or how you would actually come across a problem in this kind of question. Okay, so I'll just attach that to my software, and we're going to be continuing from here. Okay, so I hope I am recording audio as well. Okay, so this is the question. This is from 2025, paper one. Paper one. This is variant 2, and this is like the most recent one. Like that's like that has the things that I want to show it to you guys, because like it's got equations of the asymptotes and stuff like that. Okay, in it. So first of all, we want to go ahead and take a look at the format. The format is that the powers are exactly the same. If they're exactly the same, we're going to be having vertical asymptotes and horizontal asymptotes. Well, for vertical asymptotes, we got to calculate it, like if the denominator has solutions or not. If the power is like 1 greater, like if, for example, this was like 2 and this was like 3, so this was like, this would have been like 2 plus 1. This is for oblique. Okay, remember that. This is for oblique asymptote. They're the same. That means this is vertical and horizontal. If it was like 4, which is basically m plus 2, or maybe like 2 plus 2, then there are no horizontal or oblique asymptotes. There may be vertical asymptotes. So vertical asymptotes, okay? So just keep in mind these rules, and it's going to be much more easier for you. Okay, so with that being said, if you want to go ahead and calculate that, let's first calculate vertical asymptotes. Vertical asymptotes. So vertical asymptotes is specifically going to be 2x squared minus 7x minus 4 is equal to 0. And then all you got to do is kind of solve for it. So this is going to be negative 8. So what we want to do is 2x squared, 8x, just solve for it, plus x minus 4. And in an exam, just always show your steps. So that's going to be x minus 4. Then we have plus 1, x minus 4. So we have x minus 4 and 2x plus 1. Therefore, x equals 4 and x equals to minus half. This will be your vertical asymptotes. Now for horizontal asymptotes, okay, so for horizontal asymptotes, what we want to do is you could just use the formula, like just use it and that's it. So what's the formula? So I'm just going to write it in red. Is the formula is just a divided by b. Okay, what's a? So basically this is a, b, and so on, a, b, c, and so on, just like we did on the first chapter, right? But if you wanted to do it the traditional way, or kind of use the logic behind it, what we want to do is we want to go ahead and kind of it's kind of like using limits, but also not using limits. So I'm just going to go ahead and show it to you. So basically we just take or divide or multiply both by the highest power of x in both the numerators and the denominator. So 2 minus 7 over x minus 4 over x squared. Then we take the limit of y approaching infinity in both the negative and the positive direction, but let's not go into that. That's going to be more complicated. But just take, sorry, not y actually, the x. I'm sorry for that, x, because we want to check that in the axes, when it's going in the positive and the negative directions, like where is it approaching? What value of y does it want to or try to approach? That's the main goal. So we just take the limits, okay? Limits, I don't think it's a part of your further math syllabus. So if that's the case, it's like divided by infinity, 7 divided by infinity, minus 4 divided by infinity. So that's just basically 2 minus 0, 2 minus 0 minus 0, which is 2 over 2, which is 1. So therefore, the horizontal asymptote is just y equal to 1. But again, the process could be easily simplified by just using the formula. So in this case, the formula already shows that this is like 2 over 2. So this is like 2 over 2, which is 1. So you could just do it in a single line. This is only for 2 marks. And the examiner doesn't care what method you use. He's just going to check your final answer and some sort of method that you use. So we just write it as like a formula and show your workout over here. You should be totally fine. Okay, so now this question is a little bit, I don't think it's challenging, but it's a little bit more, kind of they ask more of it, is that we want to go ahead and find the stationary points of C. Okay, so cool. So what we want to do is simply just go ahead and take the function. So in this case, the function is y equal to 2x squared divided by 2x squared minus 4. Okay, so for stationary point, dy by dx is equal to 0. So therefore, dy over dx is simply just going to be v u prime minus u v prime over v squared. So we got 2x squared, 7x minus 4, 4x minus 5, 2x squared minus 5x, 4x minus 7 equal to 0. The reason is, obviously, if we solve the bottom one for 0, we're going to be ending up with our asymptotes once again. So we don't care about the asymptotes. So particularly from here, I guess, what we could specifically do is just solve for it. So yeah, let's just solve for it. So we've got 8x cubed. Again, I do know that there are going to be terms canceling out because we can see that this and this are same, so the cubes will ultimately cancel out. But let's just solve it the traditional regular way. Then you've got 10x squared. Okay. Okay. Then you've got 8x cubed. Then we've got and then okay, 20 x squared, and then what 35x is, yeah, I think that's it, right? Okay, so we cancel out a few of the terms, like they'll kind of cancel out with each other. Then we've got the squares, so we've got minus 10, 28. Oh, all of them are minuses. That's kind of funny. So we've got this, and then this is going to be a plus. I'm sorry for that. I'm sorry. And then yeah, that's going to be minus then a plus. Then you've got minus. That's also going to be turning to a plus. You've got a plus. That's going to be turning to a minus just because of this sign right here. Completely overlooks that. So that's going to be so you've got 10 minus 28. Okay. Then we're having plus 14. Plus 14. Then you've got a minus 20 squared. That's going to turn into plus 20. Okay. Minus 35. I hope my calculation's correct. This is like, and then we've got like minus 10. Yeah, then we've got minus 28. That's a positive 16, and then 20. Right. So you're going to cancel it out. So you're going to be coming up with minus 4x minus 16x. And you're going to be having a plus 20, right? This right here. So then we're just going to be changing the signs just to make the math look smarter, or whatever you call it. So over here, you could just use your calculators to solve for it. I'm going to be using a calculator just to kind of solve for the equations. This is a polynomial of degree 2, 4, 16, minus 20. So the values of x are 1 and x equal to minus 5. So when x equals to 1, so y is just going to be, I'm going to go back. So what we have is 2x squared minus 5x, 2x squared minus 7x minus 4. Oops, I kind of erased it from the calculator. 2x squared minus 5x, 2x squared. So my first value of x is going to be 1. Y is 1/3. When x is minus 5, y is going to be equal to, so you're just going to change it to minus 5. Y is going to be 25 over 27. So therefore, turning points, or whatever you call it, stationary points, are basically 1, 1/3, and minus 5, 25 by 27. So these are going to be your curves. Okay. So now sketch the stationary point, like the coordinates with stationary points over here. Now notice we've got two stationary points, right? Two stationary points. And also notice that we've got y equal to 1. Okay, so, and we have a turning point at 1. That means, oh no, sorry. We've got y equal to 1. Okay, so you've got two particular stationary points. And notice that, kind of one, actually both of the stationary points are below the horizontal asymptote. So you might be asking, okay, how does that work? Well, so remember, if we kind of go up, we did see cases where it intersects the horizontal asymptote. There might be cases for that. Okay, so you kind of have to figure that out or calculate that out. So what might happen is this could be a similar case for this as well. So let's start sketching at least. Okay. Okay, so, and this is coordinates of intersection with the line. So let's go ahead and first also find the points of intersection. So points intersection. So basically we want to say that when x equals 0, y equals what? So we've got, okay, so we will technically get 2 times 0. So you can already say that it is going to be, it's going to be a 0. So 2 is a 0, minus 5, that's a 0. Then we've also got like 2, 0, 7, 0. So we got 2, 7, that's also going to be like a 0. And then we've got another minus 4. So y equals 0 over 0. That's a 0. Okay. And then we could also say that when x equals 0, what's the particular value of y? So we know that the bottom one is obviously not going to be it because that's our vertical asymptote solution. So it's going to be basically 2x squared minus 5x equal to 0. It's like x, 2x minus 5 equals 0. So it's like x equal to 0 and x equals to 5 over 2. So we've got two intersection points right there as well. All right? Okay. So now what we want to do is let's just roughly point out the vertical asymptotes. So in this case, it's particularly going to be x is equal to 4 and x is equal to minus half. So this is minus half. And then just a little bit farther away, maybe here. x is equal to 4. And then we also have our horizontal asymptote, which is y equals 1. Now notice that we now look at the turning points, and one of them is minus 5 and 25 by 27. So it's like minus 5 and 25 by 27. So I'm assuming it's approximately somewhere here. Okay, so we've got minus 5, 25 over 27. And the other one is 1 and 1/3. So that's approximately somewhere over here. Right? 1 and 1/3. So now we got to check the behavior of the graph, right? So when x is equal to 4, so we take any value. Okay, let's say we take x equal to 5. So x equal to 5 and x equal to 6. And we want to see that how does y behave along those lines. Okay, so we want to check the behavior of the graph. So we want to take x equals to 5, and y is coming out to be 2.27. And when we take x equals to 6, I'm specifically writing decimals, it's easier to kind of visualize, y comes out to be 1.61. So the graph is going downwards. So that's the behavior of the graph. Okay, cool. So our graph is going to be something like, I'm just going to pick a different color in this case, this one. Okay, that's the first part of our graph. Next, we do know that there is a turning point over here. So obviously, this is going to be shaped like a parabola. Right? So that's one of them. Now comes the trickier part. How does this side behave? Because we have a turning point here that's below the horizontal asymptote. So again, what we simply do is we take smaller values than half. So in this particular case, let's take x equal to, let's say we take minus 2, and we take x equal to minus 3. Okay, so simply just go back to your calculator and just do minus 2 in this case. So y is 1. And when we go back to our calculator and take minus 3, this is coming out to be 0.94. So again, what what we're seeing is that the graph is on the positive side. That's one of the things to note, and it's going down. That means we're going to be having an asymptote intersection. So what we mean by that is just like we saw, that yes, this is still a turning point, but it's going to behave like this. See, it's like it asymptotes. It never reaches y, but we're simply going to be having kind of like a turning point. Now, do keep in mind that it might be the case that the graph doesn't go parabolic in every sense. What I mean by that is basically the shape might either be like, oops, sorry for that. The shape might either be parabolic, I'm going to use my laser, like this, or it might go a continuous path down. Okay, so there are two possible ways of how this could happen. Usually this is still parabolic. So what you could do is just simply draw a parabolic shape and just make a very subtle curve. Kind of like this. Okay, and that should be it. That's how it should work. Now, the following question for a single mark is just your it's the same old graph. It's just in a absolute value. And oh, we forgot to put the points of intersection. So the points of intersection that we just found out were basically you had x, 0, y, that was also 0, right? X 0, y 0. Oh, okay. Oops, I did make a mistake. Like, since x is 0, all right, just accept my drawing with an iPad for now. So basically, we've got 0, 0. That's one of them. And we have when x is 0, and when it's like 5 by 2, y is 0. Okay, so these are going to be my 2 turning points. Okay, for this one, it's exactly the same, but this is an absolute value function, so all the negative values will turn positive. That's the only change you gotta make. So what I'm just going to do is, just for making the video quicker, I'm just going to be selecting this, copying this, and I'll just paste the exact same thing here. But the only thing now we got to change is, remember that this portion remains the same. What does change is going to be this portion right here. And notice that since we just kind of redrew it, it's also intersecting our horizontal asymptote. So that's a unique property, and that could happen. But remember, for these cases, just don't check with the calculator, because you won't have enough time in your exams. Just trust the process and just flip it. That's what just happens when you're taking absolute values. So it's totally normal to happen. It might intersect the asymptotes, just don't worry about it. But it would only intersect the horizontal asymptote. Things would never intersect the vertical asymptote. If that does happen, you might have made a mistake. So just recheck in that cases. Now, these are the questions that I want to kind of talk about. Find the exact form, find an exact form, the set of values for which x intersects this. So this is something that you kind of have to gotta do with the graph, okay? And you kind of have to imagine that how things are happening, or what you specifically need to kind of do in order to go ahead and particularly solve for this problem. So in this case, it's like 1 by 9. So it's like less than that particular value. So if you go back to your graph, and if I just draw a general line, let's say 1 by 9 is below 1 over 3, which I think it should be, like, right? So it's like 1 over 3, that's like 0.3, and then 1 over 9, that's like 0.1. So let's say this is 1 over 9. So what we want to do is we want to find out the values, or the set of values for which this is less than 1 over 9, right? So it's kind of like these set of values. If I take my highlighter, these set of values. Okay, these particular set of values. So this area is going to be the shading. Okay, and also maybe, kind of this right here. Okay, so basically, now we have a visual representation of the graph. So if you just take a count and just kind of solve for the inequality as it is, okay, and we want to find the critical values. So critical values, right? So in this case, all we simply have to now kind of do is just multiply I'm just going to restart the application because for some reason it is just lagging like crazy. Okay. So we have 18x squared, and that's going to be 45x, 2x squared, 7x minus 4. So that's going to be it. Then we've got 16x squared. That's going to be 38x. And calculating, that's going to be just plus 4 is equal to 0. So we could simplify a little bit further, can't we? So 8x squared, let's go 19, if I'm not wrong. Yeah, 219, yeah. Plus 2 equal to 0. Okay. So therefore, the values of x is going to be minus 19 plus minus root over 19 squared 4ac over 2a. And then just use your calculator to kind of solve for this. Then 316 root 33. Okay, so now this is, remember, this is modulus. So again, we need to do the same thing, but this time with a negative sign. Now, you could put the negative sign anywhere. It really doesn't matter. Like, you could put it here, or you could put it on the other side. I'm going to put it on front of the 1/9 because it's, like, easier to look at, to be very honest. So that's just me, but you could do it any way you want. Okay, so that's going to be 18x squared. Then we've got the same 45, right? 45. So that's going to be 45 x. Yeah, that's it. And then we've got negative 2x squared, 7x plus 4. Okay. So we've got 20x squared, then 45, 46, 79. 52, right? 52x minus 4. Okay. So again, I'm just going to kind of make it a shortcut and just plug this entire thing in my calculator. And I get 13/10 plus minus root. Yeah, 13/10 plus minus 3√10/2. So now, notice that we've got, from the actual graph, it's going to be like 1, 2, 3, 4 intersection points. And that's totally fine. That's what we want to kind of check out, right? Now, the thing that you need to keep in mind is that where does, kind of like the graph holds valid for the particular points. So the graph from solving the inequality, for the graph, it's going to be this particular region, right? That means the inequality from graph visually is between this negative point right here and this positive point right here. So that means we're talking about this negative point right here, and we're talking about this positive point right here, right? You could even verify with the calculator by just calculating the decimal values. I've already done that on my calculator, so it's easier for me to visualize. So that means that the graph is technically valid from this particular to this particular point. So that's going to be the solution of this particular graph. It's really simple. It's how you always solve inequalities, but just you got to verify with the graph because you never know what the graph's shape is going to be. So usually they'll always give these sort of questions at the very end after you've sketched all the particulars of the graph, okay? So with that being said, this ends the entire video for rational functions. It took me a long time to put this out because I had to kind of record it in multiple stages because I was in the process of moving out and stuff. So yeah, I'll catch up in the next series of summations and the next chapter for further maths very soon. Until then, see you, and I'll catch you in the next video.